Tonight we're going into the universe, the thing we live inside, the thing that contains every star you've ever seen and every world that has ever existed, and every atom that has ever formed a thought or a heartbeat or a smile is, by almost any measure you can apply, completely and overwhelmingly empty. There is nothing out there. Not almost nothing. Not close to nothing. Nothing. And scientists have known this for decades, and they keep discovering that it's even emptier than they thought, and nobody is really talking about what that actually means. You clicked on this video because some part of you suspected the universe was hiding something. You were right. It is. It's hiding the fact that everything we think of as real, solid, present, and permanent is an almost comically thin film of matter spread across a void so total that the word empty doesn't come close to capturing it. Stay with us tonight. And please consider hitting that subscribe button as well as hitting that like button. It's a simple task, but it helps this channel reach other extraordinary minds like yours. Let's get started. Because by the end of this, you will never look at a full room the same way again. Here is the thing that no one told you in school. The universe contains roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. And yet, if you took all of that matter, every star, every planet, every asteroid, every atom of gas floating in every nebula, and you spread it evenly through the volume of the observable universe, the average density of matter would be about 1 hydrogen atom per cubic meter. 1 atom per cubic meter. To understand what that means, hold your hand out in front of you. The air between your fingers contains roughly 10 billion atoms in every cubic centimeter. The universe at large has 1 atom per cubic meter, which is a million times less dense than that. The universe is not mostly empty. The universe is almost exclusively empty, and the stuff we call reality is the exception, not the rule. This comes from decades of astrophysics research, from the measurements of the cosmic microwave background by missions like the ESA's Planck satellite, from the large-scale structure surveys of galaxies like the Sloan Digital Sky Survey, and from the consensus of the best cosmologists working today. The numbers are not in dispute. What we're going to do tonight is make sure you actually feel them. Because there's a difference between knowing something and understanding it in the way that sits with you, quietly, in the dark. We're going to start small. We're going to start with the emptiness inside the atom, which is the building block of everything you think of as solid and real. And then we're going to zoom out, layer by layer, until we're looking at the large-scale structure of the universe itself. And at each layer, the same truth will be waiting for us. Empty. 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 And the emptiest layer of all is the one that will change how you think about existence itself. But we have to earn that one. So let's start with you. You think you're solid. I understand why. You put your hand on a table and it doesn't pass through. You pour water into a glass and it stays there. You exist in a world where things feel firm and present and real, and that feeling is so consistent and so reliable that it becomes invisible. You stop noticing it the way you stop noticing the sound of a refrigerator humming. It's just there, just real, just solid. It isn't. Every atom in your body is made of a nucleus surrounded by electrons, and the ratio of the nucleus to the space around it is something that your senses are entirely incapable of communicating to you. If you took a hydrogen atom, the simplest atom, and you enlarged the nucleus to the size of a marble, about 1 centimeter across, then the electron would orbit that marble at a distance of about 530 meters. That's roughly the length of 5 American football fields, placed end to end. The marble is the nucleus. The electron is somewhere about 5 football fields away, and in between there is nothing, literally nothing. No air, no substance, no medium of any kind. Just space. Every atom is more than 99.999 followed up by 4 more nines, % empty space. Not some atoms, not most atoms, Every single atom that has ever existed, including every atom in every cell of your body as you sit here right now, is almost entirely void. The chair you're sitting on is not solid in any meaningful physical sense. It is a lattice of almost nothing whose electromagnetic fields interact with the electromagnetic fields of the almost nothing you're made of, and that interaction is what we experience as solidity. The hardness of the table, the weight of the floor under your feet, the feeling of your own hand when you press it against your face, all of it is electromagnetic repulsion between two lattices of emptiness. Nothing is touching anything. Ever. The closest things in the physical world come to each other is still separated by the vast emptiness between electron clouds. Physicists sometimes describe this by asking what would happen if you removed all the empty space from all the atoms in the human race, all 8 billion of us. If you compressed every human being on Earth to the density of an atomic nucleus, all 8 billion of us, with our bodies and our buildings and everything we've ever made, we would fit into a volume roughly the size of a sugar cube. A sugar cube. The kind you drop into a small cup of coffee. All of humanity, crushed to nuclear density, sitting on a spoon. And what's left out would be nothing, because there's almost nothing inside us in the first place. This should already be unsettling. But we haven't even left the atom yet. Because the nucleus itself, the tiny marble in the center of that vast empty atom, is not solid either. The protons and neutrons inside the nucleus are made of quarks, and quarks are held together by particles called gluons, in a way that also involves enormous amounts of empty space relative to the size of the quarks themselves. And below quarks? We don't know. Current physics can't tell us whether quarks are fundamental or whether they have structure at even smaller scales. The floor of reality, the bottom of matter, is either infinitely small or we simply can't see far enough to find it. And in either case, the emptiness goes all the way down. Let's zoom out now. Let's leave the atom and look at our own backyard. Our solar system. 8 planets, a star, countless moons, an asteroid belt, a Kuiper belt, a cloud of distant icy objects. To most people, this feels like a reasonably populated neighborhood. Maps of the solar system that we see in textbooks and posters and school classrooms show a sun in the center and a series of planets at what looks like reasonable intervals, roughly evenly spaced and comfortably close. Those maps are lying to you. Not intentionally, but completely. If you built a scale model of the solar system where the sun was the size of a basketball, roughly 24 centimeters across, Mercury would be a grain of pepper located about 10 meters away. Earth would be a small peppercorn sitting about 26 meters from the basketball sun. Jupiter, the largest planet in the solar system, would be about the size of a marble, and it would be 135 meters away. And Neptune, the outermost planet, would be a small bead sitting 778 meters from the basketball. 3/4 of a kilometer from the sun. And in between all of these tiny specks and the enormous distances between them, nothing. Absolutely nothing of substance. The solar system is a set of tiny marbles and grains scattered across an area about the size of a small city, with nothing in between but the most diffuse whisper of solar wind and scattered photons. The actual volume of the solar system, taking it out to the heliopause where the sun's influence gives way to interstellar space, is approximately 10 to the power of 34 cubic kilometers. That is a number so large that writing it out in full would require a 1 followed by 34 zeros. And all the actual matter in the solar system, all the planets and moons and asteroids and comets and dust, would fill up a tiny fraction of that volume. If you gathered every single solid and liquid object in the solar system, excluding the sun, and compressed it together, the resulting object would have less than 1/1,000,000th of the solar system's total volume. The sun itself is 99.86% of the total mass of the solar system, and yet even the sun, that enormous roaring ball of plasma, occupies a volume that represents an almost undetectable dot within the space the solar system occupies. We live in a neighborhood that is, by volume, almost perfectly empty. Now we zoom out further. Now we leave the solar system and look at the space between the stars. This is where the emptiness stops being an abstract number and starts becoming something that you might actually feel in your chest if you think about it at the right time of night. The nearest star to our Sun is Proxima Centauri, at about 4.24 light-years away. Light travels at roughly 300,000 kilometers per second, and a light-year is the distance light covers in a full year. The distance from our Sun to Proxima Centauri is about 40 trillion kilometers. To give that distance a shape you can hold in your mind, imagine the distance from the Earth to the Moon, which is about 384,000 kilometers. If you took that moon distance and laid it end to end like a ruler, you would need to stack those rulers roughly 104 million times to span the distance to Proxima Centauri. 104 million Earths to moons, laid in a chain. And in all of that space, almost nothing. A thin scattering of interstellar gas. A few stray atoms per cubic centimeter. The silence of physics operating without anything to operate on. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. That number sounds dense. It is not. The Milky Way has a diameter of about 100,000 light-years, and if you average out those 200 to 400 billion stars across that volume, the average distance between stars in our galaxy is about 4 to 5 light-years. The stars in the Milky Way are separated, on average, by roughly the same gap as the one between us and our nearest neighbor. They are not a crowded city. They are not even a sparse suburb. They are scattered like seeds dropped on a continent, each one so far from the others that no seed knows the others exist. And between those stars, the interstellar medium, a thin, thin soup of gas and dust. The density of the interstellar medium in the regions between star-forming clouds is roughly 1 atom per cubic centimeter. That sounds like something. It isn't. The best vacuum we can create in a laboratory on Earth, using our most advanced vacuum pumps, contains roughly 100,000 molecules per cubic centimeter. The interstellar medium is 100,000 times less dense than the best vacuum we can create. In a lab, when we say vacuum, we mean something emptier than empty. Space is so much emptier than that our vacuums feel crowded by comparison. Now we zoom out again, further than most people ever think. We leave the Milky Way and we look at the space between galaxies. And this is where the emptiness becomes something close to philosophical. The Milky Way is part of a group of galaxies called the Local Group, which spans about 10 million light-years and contains somewhere between 54 and 80 member galaxies. The next major cluster of galaxies, the Virgo cluster, is about 65 million light-years away. The light we see from the Virgo cluster left its source when the largest non-avian dinosaurs had only recently disappeared from Earth. That light traveled for 65 million years at 300,000 kilometers per second to arrive at your eye. And in all the space it crossed, in those 65 million light-years of travel, the average density of matter was roughly 1 hydrogen atom per cubic meter. Not per centimeter. Per meter. The intergalactic medium is 1,000 times less dense than the interstellar medium, which was already 100,000 times less dense than our best laboratory vacuum. Stand in the intergalactic void, in the enormous spaces between galaxy clusters, and what you would find is not darkness in the way a dark room is dark. A dark room is full of air, full of molecules, full of physics happening constantly. The intergalactic void is a place where, if you extended your hand, the nearest atom might be a cubic meter away. The nearest cubic meter of space containing even 1 atom would be the most concentrated thing in your environment. There would be no temperature you could feel because temperature requires matter to carry it. There would be no sound because sound requires a medium to propagate. There would be no wind, no pressure, no sensation of any kind because all sensation requires matter interacting with other matter, and in the intergalactic void there isn't enough matter in reach of your body to produce any sensation at all. It would be like trying to feel humidity in a room where the nearest water molecule was on the other side of the building. Except the building is millions of light years wide. Between galaxy clusters, there are regions astronomers call voids. The Bootes void, one of the most famous, is roughly 250 to 330 million light-years across, which is a span so large that if you tried to cross it at the speed a commercial airliner cruises, roughly 900 kilometers per hour, it would take you about 350 billion years. The current age of the universe is 13.8 billion years. The crossing time for the Bootes void at airliner speed would be 25 billion times the age of the universe. The Bootes void contains almost nothing. A handful of galaxies where you'd expect to find thousands. A region of space so empty that when astronomers discovered it in 1981, they initially thought there must be an error in their data. There wasn't. Here is where the story gets strange in a new direction. Because the emptiness isn't random. The voids, the vast empty regions of the universe, are not scattered like potholes in a road. They are organized. They are structured. The universe, on its largest scales, has a pattern. And that pattern is one of the most alien things science has ever shown us about the place we live in. Astronomers mapping the large-scale distribution of galaxies have discovered that galaxies are not spread evenly through space. They are not scattered randomly like seeds in wind. Instead, they cluster along enormous filaments, long string-like structures of gas and dark matter that stretch across hundreds of millions of light-years, intersecting at nodes where the densest clusters of galaxies form. Between these filaments are the voids. The whole structure, the filaments and nodes and voids together, is called the cosmic web. And it looks, in the images produced by galaxy surveys and computer simulations, almost exactly like a biological neural network, like a brain. Like the structure of neurons and synapses rendered at cosmological scale. The cosmic web was first theorized in the 1970s and confirmed through large-scale surveys of galaxy positions over subsequent decades, most definitively by the Sloan Digital Sky Survey, which mapped the positions of over 1 million galaxies and revealed the filamentary structure in extraordinary detail. The filaments themselves are not thin threads. They are structures tens of millions of light-years in diameter, filled with diffuse gas and dark matter, and connecting the galaxy clusters the way rivers connect lakes. But here is the part that changes the picture. By volume, the voids, the empty regions, account for approximately 80% of the total volume of the observable universe. 80%. The cosmic web, with all its filaments and clusters, all the places where galaxies actually exist, accounts for about 20% of the volume. But even that 20% is not dense. Even the filaments, in absolute terms, contain almost nothing. The matter in a cosmic filament is still, per cubic meter, not much more than the average intergalactic void. It's just enough more to allow gravity to accumulate it into galaxies over billions of years. But here's what makes the emptiness stranger. The structure you just heard about, the cosmic web, is not made primarily of the matter we can see. It's made of something we cannot see, cannot detect directly, cannot sample, cannot touch in any way we currently know how to. Dark matter. The skeleton on which the visible universe hangs. Dark matter is believed to make up about 27% of the total content of the universe. All the ordinary matter, everything made of atoms, every star, every planet, every human being, every spacecraft we've ever launched, all the gas in the intergalactic medium Everything you can see or touch or measure represents about 5% of the universe's total content. Dark matter is more than 5 times as abundant as ordinary matter. And it does not interact with light. It doesn't shine. It doesn't reflect. It doesn't absorb. It passes through ordinary matter almost without effect, as if ordinary matter were the ghost and dark matter were the real thing. Right now, as you read this or listen to this, dark matter particles are passing through your body. Tens of thousands of them, every second, traveling through the planet and through you as if you weren't there. Your body is, from dark matter's perspective, no more substantial than a ghost. You are mostly empty space filled with electromagnetic interactions that mean nothing to a dark matter particle. The dark matter flows through you, through the floor, through the earth, through the entire planet, without slowing, without interacting, without leaving any trace. We have been trying to detect individual dark matter particles in dedicated underground laboratories, shielded from cosmic rays and other backgrounds for decades. As of today, we have not successfully detected a single one. We know dark matter is there because of gravity. We can see its gravitational fingerprints. Galaxies rotate in ways that don't make sense if only their visible matter were present. The stars in the outer arms of spiral galaxies orbit at the same speed as stars near the center, when physics predicts they should orbit much slower. The only explanation that works is a vast halo of invisible matter surrounding each galaxy, providing extra gravitational force. Clusters of galaxies bend light from objects behind them more strongly than their visible matter can account for, again implying a large invisible mass component. The way the cosmic web itself formed, the filamentary structure we just talked about, can only be reproduced in computer simulations if you include dark matter. Without it, the models produce a universe that looks nothing like the one we actually live in. So the true skeleton of the universe, the structure on which everything visible hangs, is invisible. The filaments of the cosmic web are primarily dark matter filaments, with ordinary matter clumping along them the way beads collect along a thread. The galaxies we see are not the universe's structure. They are the universe's decorations, markers on an invisible map. And the map itself is made of something we cannot touch, see, or directly detect. The universe is not only empty of visible matter, it is full of invisible matter that we cannot yet understand. And that, as it turns out, is still not the strangest ingredient. In 1998, 2 independent teams of astronomers doing what seemed like routine observations of distant supernovae discovered something that neither team had expected, that nobody had predicted in quite the way it turned out, and that permanently altered the standard model of cosmology. They discovered that the expansion of the universe, instead of slowing down under gravity as everyone expected, is accelerating. The universe is not just expanding. It's expanding faster and faster. Something is pushing it apart, and we have no idea what that something is. We have named it dark energy, which is really just a label we put on our ignorance, and it constitutes about 68% of the total energy content of the universe. Think about that composition for a moment. 5% ordinary matter, everything you can see, touch, or measure. 27% dark matter, invisible but at least gravitationally familiar. 68% dark energy, which we know almost nothing about beyond the fact that it's causing the universe to accelerate apart. We understand the minority ingredient, the stuff we're made of, with enormous precision. We understand the slightly larger ingredient, dark matter, well enough to know its effects. But we are mostly in the dark about the dominant ingredient. 68% of the universe is something we genuinely do not understand. And dark energy's effect is to make the emptiness worse. Because the universe is accelerating apart, the voids are growing. The distances between galaxy clusters are increasing. The most distant galaxies are already moving away from us at speeds exceeding the speed of light, not because they're moving through space, but because space itself is expanding between us and them, carrying them further and further away. In the far future, billions of years from now, those galaxies will have expanded past the cosmic horizon, the distance beyond which their light can never reach us, and they will, from our perspective, cease to exist. The night sky will gradually dim, galaxy by galaxy, cluster by cluster. The emptiness will grow, and nothing we can do will stop it. The universe is not settling towards some equilibrium. It is not finding a comfortable density and pausing there. It is relentlessly, unstoppably expanding, and every moment that passes, the emptiness between things gets slightly, permanently larger. The universe we live in today, with all its galaxies visible in telescopes, all its structure readable in surveys, is actually one of the most galaxy-rich times that ever will exist. Future civilizations, if any exist in the far future, will look out at a sky that contains progressively less. They will be more alone than we are. The universe is becoming emptier as we watch. You might be tempted at this point to say, fine, but the void is still filled with something. The vacuum of space isn't truly empty, is it? And this is where physics becomes genuinely strange. Because you're right. The quantum vacuum, what we call empty space at the quantum level, is not truly empty. It is filled with something called vacuum energy, a seething, roiling sea of virtual particles that pop in and out of existence on timescales so brief that they are, in the strict quantum sense, undetectable as individual events. Quantum mechanics, specifically the Heisenberg uncertainty principle, means that empty space is not allowed to be truly empty. The energy of a region of space cannot be exactly zero, because if it were, you'd know both the energy and the time with perfect precision, which violates the uncertainty principle. So even perfect vacuum has a baseline energy, a lowest possible state that is still not zero. And at that lowest state, particle-antiparticle pairs are constantly flickering into existence and annihilating each other almost instantly, too briefly to be detected individually but real in the sense that their aggregate effects can be measured. One experiment that reveals the vacuum energy is the Casimir effect. If you take two uncharged metal plates and place them extremely close together in a vacuum, they attract each other. Not because of gravity, which would be negligibly small at that scale, and not because of electromagnetic charge, because they're uncharged. They attract because the quantum vacuum between the plates is slightly different from the vacuum outside the plates. The close spacing of the plates limits which virtual particles can form in the space between them, so there are fewer vacuum fluctuations between the plates than outside, and the imbalance creates a pressure that pushes the plates together. An effect caused by nothing except the geometry of empty space and the quantum rules governing the energetics of nothing. The Casimir effect has been measured experimentally. It is real. Empty space has energy. But here is where it gets uncomfortable. Physicists calculate the amount of vacuum energy based on quantum field theory and get a number. Then they measure the amount of dark energy that's causing the universe to accelerate and get another number. And these two numbers, which should be related and are probably the same thing seen from two different perspectives, differ by a factor of roughly 10 to the power of 120. A 1 followed by 120 zeros. To convey the magnitude of that discrepancy, consider this. The number of atoms in the entire observable universe is estimated at roughly 10 to the power of 80. The discrepancy between our theoretical calculation of vacuum energy and our measured value of dark energy is a trillion times larger than the number of atoms in the entire observable universe. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of science. Physicists call it the cosmological constant problem. It is also in the running for the most honest thing you can say about it, the biggest unsolved problem in all of physics. Here is the part that sits with you longest if you let it. The universe has a future, and that future is the story of increasing emptiness, played out over time scales that make the current age of the universe look like the first few pages of a very long book. Right now, the universe is 13.8 billion years old. We are at what astronomers describe as a relatively early and active era. Stars are forming, galaxies are colliding and merging, planets are forming around new stars. Life, presumably, is appearing and developing in at least some corners of the cosmos. We are in what might be called the peak of the universe's activity. But this peak will end, and the end is already visible from where we stand. In about 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, consuming Mercury, Venus, and possibly Earth before shedding its outer layers and collapsing into a white dwarf. A white dwarf is roughly the size of the Earth but contains the mass of the Sun. If the Sun shrank to the size of a marble, a white dwarf of the same mass would be a pea. That white dwarf will then cool over hundreds of billions of years, growing dimmer and dimmer until it becomes a cold, dark, inert object called a black dwarf. The universe is currently not old enough for any white dwarf to have cooled to that point. Every black dwarf that will ever exist is still in the future. Over the next 100 billion years, the rate of star formation across the universe will decline. The supply of cold gas that forms new stars is being exhausted. New stars will become rarer. Existing stars will age and die. The universe will gradually dim. The era we're in now, sometimes called the stelliferous era, the age of stars, will give way to what cosmologists call the degenerate era, a time dominated by the remnants of dead stars. White dwarfs and neutron stars and black holes will inherit the universe, and the light will slowly go out. In about 10,000 trillion years, which you could write as a 10 followed by 16 zeros, even the smallest and longest-lived red dwarf stars will have burned out. The universe will be populated mostly by cold, dead stellar remnants and black holes. In the darkness, there will still be rare, dim flickers. Occasionally, two brown dwarfs, failed stars that never ignited, will collide and merge with enough mass to trigger fusion, briefly lighting up like a candle in an enormous dark room before burning out again. But these will become rarer and rarer. The universe will be growing toward a silence that has no human analogy. And then the black holes. In the very far future, in timescales that require new words to describe because our standard ones run out, black holes will slowly evaporate through a process called Hawking radiation. A black hole, even in perfect vacuum, is not perfectly stable. Near its event horizon, quantum fluctuations allow pairs of virtual particles to form in which one particle falls in and one escapes. Over inconceivably long timescales, this causes the black hole to lose mass and eventually evaporate entirely. A black hole the mass of our Sun would take roughly 10 to the power of 67 years to evaporate. A supermassive black hole, the kind that sits at the center of galaxies, would take approximately 10 to the power of 100 years. That second number is called a googol. It's where the name Google comes from. A googol years. In a googol years, the last black holes will have evaporated, and the universe will contain almost nothing but a thin, cold sea of photons and elementary particles, all at the same temperature, all infinitely diluted across a space that has been expanding for longer than you can imagine. This is the heat death. Maximum entropy. The end of all structure. The quietest possible state. There's a specific flavor of the emptiness that hits differently when you apply it to the question of life. And it goes by the name of the Fermi paradox, which is less a paradox than a question that keeps returning in the dark when you least expect it. In 1950, Physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory and, in the middle of a conversation about alien life, asked a question that has never been fully answered. Given the size of the galaxy, the age of the universe, the number of stars, the number of planets likely orbiting them, and the billions of years of head start some of those planets have had on Earth, where is everyone? The galaxy is estimated to be about 13.5 billion years old. That's nearly the age of the universe. Stars with planets have existed for most of that time. If even one civilization had emerged somewhere in the Milky Way a billion years before us and achieved spacefaring capability and expanded at even a small fraction of the speed of light, they would have had time to colonize every star in the galaxy many times over. They would be everywhere. And yet, nothing. Silence. The emptiness of the sky, when listened to for signs of intelligence, has returned nothing confirmed, nothing unambiguous, nothing we cannot explain as natural phenomena. The numbers underlying this are worth sitting with. The Milky Way contains somewhere between 200 and 400 billion stars. Studies of planets around other stars, from missions like NASA's Kepler telescope, suggest that roughly every star has at least one planet, and that somewhere between 10 and 40% of Sun-like stars have a planet in the habitable zone, the orbital distance range where liquid water could exist on the surface. Even at the conservative end, that's tens of billions of potentially habitable worlds in just our galaxy. And our galaxy is just one of 2 trillion in the observable universe. The number of potentially habitable worlds in the observable universe is a number so large that writing it in standard notation would take multiple pages. And yet, silence. We have been listening systematically since 1960, when astronomer Frank Drake pointed a radio telescope at 2 nearby Sun-like stars and listened for artificial signals. The SETI, Search for Extraterrestrial Intelligence program, has been running in various forms for over 60 years. We have scanned millions of star systems. We have searched multiple frequency ranges. We have analyzed enormous amounts of data. And we have found exactly one candidate signal worth discussing, the WOW signal detected by astronomer Jerry Ayman in 1977 at the Big Ear Radio Observatory in Ohio. A signal that lasted 72 seconds, matched the predicted characteristics of an artificial transmission precisely, and has never been detected again despite repeated searches of the same region of sky. One signal. In 60 years. From 2 trillion galaxies each with hundreds of billions of stars. The emptiness of the sky when we listen is as complete as the emptiness of the space between stars. And that either means we are alone, which has its own weight, or it means something else. Something that has been given names like the Great Filter, the Dark Forest Hypothesis, or the simple and devastating possibility that civilizations like ours simply don't last. That the galaxy is full of the ruins of civilizations that burned brightly and went quiet before they could announce themselves. The silence is not reassuring. It is one of the most unsettling kinds of empty. The Great Filter is a concept introduced by economist Robin Hanson in 1998 and developed since by thinkers across multiple fields. It starts with the observation that life, or at least intelligent technological life, appears to be absent or extremely rare in the observable universe, despite the enormous number of potential locations where it could have developed. The Great Filter is whatever barrier, or series of barriers, makes the emergence and persistence of technological civilizations so improbable that they are effectively absent. The filter could be behind us. The emergence of life itself might be the hard step. The jump from non-living chemistry to self-replicating molecules, the origin of life, might be so improbable that it has only happened once, or a handful of times, in the entire observable universe. Alternatively, the development of complex multicellular life might be the filter. Life on Earth existed for roughly the first 3 billion years as single-celled organisms. The development of eukaryotic cells, cells with a nucleus, which are the building block of all complex life, was a specific event that might be fantastically improbable. The development of sexual reproduction, of complex animal body plans, of nervous systems, of intelligence, any one of these transitions might represent a step so unlikely that it serves as a nearly insurmountable barrier. Or the filter might be ahead of us. And if that's the case, the silence is a warning. Because a filter ahead of us means that civilizations that reach our level of technological development tend, for some reason, not to survive much longer. They might destroy themselves. Through weapons, through environmental collapse, through the misuse of technologies that were beyond their wisdom to handle. Or they might be destroyed by something external. A gamma ray burst from a nearby star, sterilizing a civilization's planet without warning. A pandemic. An asteroid. The universe has many ways to silence a voice. But here is the thought that makes the great filter genuinely unnerving in the context of emptiness. The cleaner the sky, the more complete the silence, the further the filter might be ahead of us. If we searched the universe and found it full of simple life, bacterial mats on Mars, microbes in the oceans of Europa, algae on some distant moon, it would suggest that simple life is easy, that the filters beyond it are what's hard. But we've looked at Mars and found nothing yet. We've probed its soil and analyzed its atmosphere and sent rovers to explore its ancient riverbeds and dry lake beds. The silence of Mars is not the silence of confirmed absence. We haven't looked everywhere, and we might have missed it. But the silence so far is what it is. The universe is empty in many different ways simultaneously. Empty of matter by volume. Empty of signals from other minds. And possibly, terrifyingly, empty of anything that resembles us for billions of light years in any direction. We might be the only conversation this galaxy is having with itself. Let me slow down here and let some of this settle. Because what we've been doing for the last several chapters is accumulating a picture, layer by layer, of a universe that is almost entirely nothing. And I think it's worth asking what that actually means for the experience of being alive. Not in a bleak way. Not in a hopeless way. But honestly, everything you are is made of atoms that are mostly empty. Those atoms are part of a planet that is a tiny rock orbiting a star that is a tiny point in a galaxy that is itself a thin film of matter stretched across a void. That galaxy is one of 2 trillion and 2 trillion galaxies, for all their collective billions of stars, still leave 80% of the observable universe completely empty. And the whole structure is embedded in a space that is expanding, driven by a dark energy we don't understand, growing emptier by the moment. You are, by almost every objective measurement, an almost infinitely small thing existing in an almost infinitely empty place. And yet, you are reading these words, or hearing them, processing them, feeling something about them, some combination of curiosity and unease and something that might be awe. Your brain, that 3-pound mass of electrochemical activity sitting in your skull, is doing something that nothing else in the known universe demonstrably does. It is making meaning out of information. It is connecting the distances to something it cares about. It is wondering. Not just processing. Wondering. The cosmologist Carl Sagan wrote decades ago that we are a way for the cosmos to know itself. What he meant was that the matter that formed in the Big Bang, the hydrogen and helium that condensed into stars, the heavier elements forged in stellar cores and scattered by supernovae, the carbon and oxygen and nitrogen and iron that eventually wound up in oceans and atmospheres and living cells and nervous systems, all of that matter has now, through us, produced something capable of understanding what it is and where it came from. The universe has been around for 13.8 billion years. For most of that time, it was empty in every sense. No one was watching. No one was counting the galaxies or measuring the voids or wondering about the silence. The matter just was, following the rules of physics with no awareness of itself. We changed that. Something in us changed that. And the change is so recent in cosmic terms that it barely registers. Modern Homo sapiens have existed for maybe 300,000 years. We've had science for a few centuries. We've known about other galaxies for less than a century. In the 13.8 billion year history of the universe, our moment of knowing is shorter than the last word of the last sentence of a very long book. And yet it happened. And it is, from where I'm standing, the strangest and most extraordinary thing about the universe. That matter eventually arranged itself into something that could be surprised by its own arrangement. There's a layer of this that we haven't talked about yet, and it's the one that might be the hardest to sit with. Because everything we've described, the voids between galaxies, the emptiness between stars, the space inside atoms, it all has structure. It all has a geometry. The cosmic web is a structure. The atom is a structure. The emptiness is defined by the matter around it. The void exists in relation to something. But what about the emptiness that has no structure around it? What about the regions of the universe beyond the observable horizon, beyond the sphere of space from which light has had time to reach us? We cannot see them. We cannot measure them. We cannot even in principle know what they contain. And the leading models of cosmology, the inflationary models that describe what happened in the first trillionth of a second after the Big Bang, strongly suggest that the universe extends vastly beyond what we can observe. Some versions of inflationary theory predict that the universe is infinite, that the 93 billion light-year diameter bubble of space we can observe is an infinitesimally small region of an infinitely large whole. If the universe is infinite, then every possible configuration of matter that physics allows exists somewhere. Every planet, every civilization, every outcome. An infinite universe contains infinite versions of everything, including, somewhere, copies of you, making different choices, living different lives. This is not mysticism. This is a straightforward consequence of infinity combined with a finite number of possible quantum states in any finite volume. If you have infinite space and a finite number of distinct arrangements of matter per unit volume, eventually every arrangement repeats. Eventually, the atoms in a region of space arrange themselves into an exact duplicate of the observable universe, including you reading this at this moment. An exact copy. Except that copy is so far away that the distance cannot be expressed in any unit we currently use. This idea, sometimes called the Level 1 multiverse by physicist Max Tegmark, is not science fiction. It is the logical consequence of the most successful cosmological theories we have, applied without flinching. And it makes the emptiness simultaneously worse and strange in a new direction. The void is not just between things. The void might be infinite. And within the infinite void, our entire observable universe, all 2 trillion galaxies of it, might be so small relative to the whole that it's smaller than a single atom compared to a planet. We cannot know. The physics of our observable universe doesn't give us a way to look over the horizon. The cosmic microwave background, the farthest light we can see, is the surface of last scattering from 380,000 years after the Big Bang. Beyond it, even in principle, we cannot see. The universe has an edge past which it is forever hidden from us. The emptiness of space and the emptiness of the future are connected by something we experience every day and understand very poorly: time. The universe's emptiness is not a static condition. It's a process. The void is not just where matter isn't. The void is where matter used to be and where matter is heading. Entropy, the fundamental tendency of physical systems toward disorder, toward maximum possible randomness, is the engine of the universe's growing emptiness. In any closed system without external energy input, entropy increases. Structure breaks down. Order dissolves into disorder. Energy spreads from concentrated to dilute. Heat flows from hot to cold. Information degrades. And on the cosmic scale, the universe is a closed system, and its entropy has been increasing since the Big Bang. The Big Bang itself was a state of extraordinarily low entropy. Everything compressed into an almost infinitely small, almost infinitely hot region. All the energy in one place. And since then, the universe has been a long, slow, relentless spreading. Energy flowing outward, matter dispersing, structure forming temporarily in stars and galaxies and planets and life, but always as local exceptions to the global trend. Eddies in a current that is always flowing toward the same destination. Maximum entropy. The heat death. The quiet. We are living in a cosmically brief moment of low enough entropy that complexity is possible. That stars can burn. That chemistry can happen. That life can organize itself and sustain itself against the entropy gradient. We are running against the current. Not forever, but for now. And the question of whether we matter, whether our moment of knowing the universe is something the universe notices or cares about, is a question the universe is not equipped to answer. It will keep expanding regardless. The voids will keep growing. The entropy will keep increasing. The fire of awareness will persist as long as it can, and then it won't, and the universe will keep going, vast and cold and patient for a time that makes our existence feel like a single breath in the history of a mountain. I want to offer something before we get to the end, because I don't think the emptiness is only unsettling. I think it's also, if you come at it from a certain angle, one of the most beautiful things about existence. The universe is almost entirely empty. That means that matter, when it comes together, is doing something extraordinary against enormous odds. Every star is a local victory against the void. Every planet is matter asserting its own complexity in a cosmos that is mostly nothing. Every organism is physics performing an almost impossible trick, assembling information against entropy, maintaining order in a universe committed to disorder, persisting in an environment that is, at every scale, mostly empty and mostly cold and mostly ancient and mostly silent. You exist in defiance of the statistics. The hydrogen atoms in your body are, most of them, as old as the universe. They formed in the first 3 minutes after the Big Bang, and for the first 10 billion years of cosmic history, they were just gas. Drifting. Dispersed. Carried in the thin currents of the intergalactic medium. Then they ended up in a nebula, then in a star, then in a supernova, then scattered, then gathered again. Eventually, through a chain of events so improbable it barely seems like a coherent narrative, they ended up in a planet, and then in an ocean, and then in a molecule, and then in a cell, and then in a body, your body, and here they are, now, arranged in a configuration that is capable of reading these words and feeling something about them. That is not a small thing. The emptiness is the context that makes presence meaningful. If the universe were full, uniformly dense, a solid block of matter from one end to the other, nothing could exist in it. No structure, no chemistry, no complexity, no life. The void is not the opposite of meaning. The void is the space in which meaning is possible. Stars need the emptiness to shine into. Planets need empty orbits to maintain them. Life needs the quiet of mostly empty space for the precisely calibrated conditions of one small world to persist. The emptiness makes us possible. There is one more kind of empty we should talk about, because it is the emptiness we are surrounded by right now, and almost no one ever thinks about it. Right now, as you exist in whatever room or vehicle or outdoor space you're in, you are bathed in the cosmic microwave background radiation. It is arriving at your body from every direction simultaneously. You cannot feel it. You cannot see it. Your body cannot detect it in any way. but it is there, permeating everything, filling the universe uniformly from edge to edge. The cosmic microwave background is the afterglow of the Big Bang. In the first 380,000 years of the universe's existence, matter was so hot and dense that photons couldn't travel freely. The universe was opaque. Then, as it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms for the first time, and suddenly the universe became transparent. The photons that had been trapped in the hot plasma were released. They flew outward in every direction. They have been flying ever since, for 13.8 billion years. And they are arriving at your body right now. They are not hot anymore. The expansion of the universe has stretched them, red-shifted them, cooled them from the incandescent billions of degrees they once carried to a temperature of just 2.725 Kelvin, about 270 degrees below the freezing point of water. They are the coldest and oldest light in the universe. They predate every star. They predate every galaxy. They predate every atom heavier than hydrogen. They were released when the universe was 380,000 years old, and they have been traveling ever since. And they fill space so uniformly, so completely, that wherever you point a sensitive microwave detector, you find them. There is nowhere in the observable universe where they are not. The cosmic microwave background was discovered accidentally in 1965 by radio astronomers Arno Penzias and Robert Wilson, who were trying to use a large microwave antenna in New Jersey to study the Milky Way. They kept finding a persistent background noise they couldn't eliminate. They cleaned the antenna, removed bird droppings, checked their equipment repeatedly. The noise persisted. It came equally from all directions. It was the echo of creation, 13.8 billion years old, arriving at a microwave dish in New Jersey. Penzias and Wilson won the Nobel Prize in Physics in 1978 for the discovery. And the thing they discovered is permeating you right now. Ancient light, from before stars, from the first moment of the universe's transparency, passing through you quietly as you sit wherever you are, in the middle of whatever ordinary moment this is. So here we are. You know that the universe is, by volume, almost completely empty. You know that the matter in it, all of it, including everything you've ever seen and everyone you've ever known and every place you've ever been, is a thin and improbable exception to a rule of absolute emptiness. You know that the emptiness is growing, driven by dark energy we don't understand. You know that the sky is silent, offering no confirmation that anything resembling us exists anywhere else. You know that the future of the universe is toward maximum entropy, a state of such total disorder that complexity, life, thought, and meaning become thermodynamically impossible. And you know that you are, right now, at this precise moment, alive in the narrow sliver of cosmic history where conditions are hospitable for something like you. What do you do with that? There isn't a universal answer. But I think the honest answer, the one that doesn't flinch, involves staying with the discomfort of the scale long enough to come out the other side of it. Because on the other side of that discomfort is something that functions like clarity. The universe is almost entirely empty. You are almost entirely empty. You are, in the most precise physical sense available to us, almost nothing. And you are here, thinking, feeling, wondering. Made of the oldest atoms in the universe, assembled in the most improbable configuration, alive in the most hospitable window, aware of the void that surrounds you and the void that constitutes you, and capable of caring about all of it. That is the thing I keep coming back to. Not the scale, not the distances, not the cold mathematics of entropy, but the fact that somewhere in a mostly empty universe, atoms gathered themselves into something that can feel the weight of the emptiness and be moved by it. that is not nothing. That is, as far as we can tell, everything. Here is the payoff. Here is what all of this has been building toward. The universe is empty in every direction and at every scale we can examine. It is emptier than intuition can reach. It is becoming emptier every moment. And the silence we hear when we listen for other minds is part of that emptiness. We exist in a cosmos that is, by almost every measure, not designed for us, not hospitable to us, not aware of us, and growing steadily less habitable as it expands toward its cold and final quiet. And you are here anyway, living inside the smallest possible fraction of the universe's volume, alive at the smallest possible fraction of the universe's age, made of matter so rare and improbable that the laws of statistics would never have predicted it. You are the universe's longest shot, and you pulled it off. Every morning you wake up, you are a temporary refusal of the entropy that has been trending since the first second. You are the universe doing something it almost never does, being aware of itself, being curious about itself, caring about the distance between things. The atoms in your hands, the ones that were hydrogen gas in the universe's first 3 minutes and then were forged into heavier elements in a star that exploded before the sun existed. Those atoms spent billions of years drifting through the nothing, carried by filaments of dark matter, building toward galaxies, building toward chemistry, building toward the improbable chain of events that produce this moment. And this moment, this specific awareness of the emptiness, is something those atoms have never done before and may never do again. The universe is empty, but you are not. And there is a question waiting just past the edge of this one, a related and even stranger emptiness that we haven't touched today. Because if the universe is expanding and the matter within it is spreading apart, and the voids are growing and entropy is increasing, then the question of where it all came from, how something this vast and this empty emerged from nothing at all, from a state of even more total emptiness than what exists now, is a question that cosmologists are still working through. The Big Bang didn't emerge from empty space. It emerged from nothing, not from a vacuum, from genuinely nothing, no space, no time, no physics, no rules. And the question of how something comes from nothing in that absolute sense is one that science is only beginning to approach, and the answer, when it comes, will probably change everything again. That's the next video. And if this one left you sitting in the quiet for a moment, that one will take you further in.